Okay. Greetings to you all. Welcome to this very important webinar that will be given by Professor Achim DOBERMANN. Achim is the chief scientist of the International Fertilizer Association, IFA, based in Paris, France. As a chief scientist, Achim provides strategic scientific advice to IFA and its members on promoting responsible plant nutrition and enhancing nutrient stewardship worldwide. Achim has served as director and CEO of the Rothamsted Research in the UK from 2014 to 2019, as Deputy Director General of the International Rice Research Institute, IRI, in the Philippines from 2008 to 2014. And he has also served as Professor of Soil Science and Nutrient Management at the University of Nebraska, Lincoln in the United States of America from the year 2000 to 2007. And as a soil nutrient specialist at IRI from 1992 to the year 2000. Achim received his MSc degree in tropical agriculture and PhD in soil science from the University of Leipzig in Germany. Dr. Dobermann has over 30 years of field experience working in every region of the world on science and technology for sustainable farming, with particular emphasis on soil science, plant nutrition, and agronomy. He has published on a wide range of agricultural issues and also leads a massive open online course on feeding a hungry planet, agriculture, nutrition, and sustainability. He serves on the board of ISDA Limited and Agri-Metrics Limited, two startups working on data-driven solutions for agronomy and farming, or on several scientific advisory bodies in Africa, Europe, Asia, and South America. He chairs the scientific committee of the agrobioscience program of ATUM 6P, and we are honored with that. And he's also a member of the scientific advisory committee of the African Plant Nutrition Institute, APNI. We are very honored to have you, Professor Dobermann, for this seminar. We thank you for having accepted to devote some time to share your knowledge with our students, faculty, and staff, and all our friends from Reforum and from a number of countries on the African countries, the African continent, and maybe in some other parts of the world. So we'll see them popping on the screen if they ask you questions. So Professor Dobermann, the floor is yours.
Well, thank you for this.
40 minutes presentation, and then 20 minutes Q&A session. Thank you.
Good. Thank you for that introduction. It's getting a bit long, but my interest, as you can see from this title, is in plant nutrition, but a broader view, a more food systems and circular economy view of plant nutrition, which I think is much broader than what we normally used to learn in the textbooks on crop nutrition and soil fertility. So that's what I want to talk about today, and then at the end I'll make some remarks about Africa too. So what I present here is also on behalf of a new scientific panel on responsible plant nutrition. We are 11 experts who represent different regions in the world and different areas of scientific expertise. And in late last year, we worked on a document with this title. And most of what I present today is a summary of what we are discussing in this paper. Now, I want to start with a historical view. And as you've heard, I also was the director of Rothamsted Research in the UK. And Rothamsted is famous for having the oldest long-term experiments in the world still running. And the first one and the oldest and most famous one is this one here, the Broadbork wheat experiment, which has been running since 1843. And it was also one of the key experiments that demonstrated very early on already the value of nutrients, nitrogen, phosphorus, potassium, and even in this case, some others. So you can see in this graph, these are 5-year averages of wheat yield, wheat grain yield. The blue line is without any fertilizer and also no manure, and it's continuously growing wheat. So essentially, we have a yield of about 1 ton, and it didn't matter whether you changed the cultivars over time. As you can see down here, these are the names of the different varieties grown over time. You have a purple line here, or the pink line, whatever you call it, that is, which is a high dose of farmyard manure. So that immediately doubled or tripled the yield. And this dark blue line here is a treatment that receives a balanced application of mineral nutrients, so mineral fertilizer. And you can see for the first 100 years or so, that treatment yielded exactly the same as the farmyard manure. So for a plant, it doesn't make a difference where the nutrients are coming from what sources, as long as there is enough of them. But this experiment also shows very well what we later became all familiar with as the Green Revolution. So you can see here in the 1960s, the first high-yielding variety, Capel, was introduced, which had a much higher harvest index and therefore also responded much better to nutrient application. And so the yield immediately doubled from 3 to 6 tons with fertilizer and manure. And if then later wheat was grown in crop rotation and followed other crops, you could, over the years, through other implementations of technology changes, different forms of fertilizers, higher nitrogen rates, different timing of nitrogen rates. There were other advances. Herbicides came along and fungicides and so on. So a succession of improvements that nowadays allow us to reach, in recent years, wheat yields of about 12 tons per hectare on a consistent basis in the best treatments with best fertilizer. But we also get the same yields with the high dose of manure and a little bit of extra nitrogen. So this is the general trajectory of intensification of agriculture that has happened in various ways in most parts of the world. And I was 16 years old when I entered this. You can see in 1977, when I was 16, we were right in the beginning or middle phase of that intensification here, anywhere in the world, And I was living in East Germany, and so under the communist regime, intensification looked like this. So big machines, intensive tillage, lots of fertilizer applications and spraying, fertilizer spreading machines even made it on the postage stamps in my country. You can see those here. And big machines for harvest and other kinds of operations. Big fields, big machines, heavy loads of inputs. It was an exciting time for young people because we thought that this is the future of farming. This is how modern agriculture looks like. It's going to be technology driven. It's going to be industrialized, in some form, But the problem is that, of course, now we know that this form of agriculture, this type of intensification, also caused all kind of issues and problems, which we only became aware later. In recent years, I think, therefore, the realization has kicked in that we need to look at agriculture in a much more sustainable manner. And for plant nutrition, this also means that we, besides having to produce enough food and also high quality food and nutritious food, We also need to do this in a way that reduces greenhouse gas emissions, sequesters carbon in the soil, avoids pollution and other impacts on biodiversity, has less waste and improves nutrient cycling, and in general also can have other contributions to specific forms of human nutrition and human health. So these are the elements of the new paradigm. And in the fertilizer industry, we started discussing these already several years ago and produced a little document as part of an outcome of a high-level forum in 2019, in which many of these things are already stated. So in the scientific panel, we then spent several months last year discussing these elements in more depth, and particularly also looking at them from a scientific point of view. So what are actually some of the challenges that we need to tackle? What can be done about those? Who would need to do what? And if we succeed, what would success look like? So I'll be talking about some of these things, but you can also go to this website, sprpn.org, to actually download the paper, and there's also some other materials there. So the first issue that we identified is this one here. And it's this question of how we in the future can decouple the growth in food production that is needed because world population is still growing and people eat more food. The growth in crop production in particularly, how can we decouple it from further growth in fertilizer consumption? So in the past, as you can see here, this is a graph showing on the x-axis time since 1960s, and on the y-axis different components of the global cropland nitrogen budget. So on cropland, we're not including livestock production or grassland systems here. And you can see that the brown dots here is the increase in cropland nitrogen output, so that's yield. So has more than doubled, of course, or nearly tripled over this time, but at the cost of also a much faster growth in nitrogen inputs. You can see the orange line here, and that is mostly fertilizers, although, of course, inputs nitrogen in the form of manure and biological nitrogen fixation have also increased. But as you can see, the rate of growth in this line is steeper than the rate of growth in this line. And if we were to continue this on a global scale for more decades to come, we further increase the load of nitrogen, of reactive nitrogen, into the global ecosystem, and therefore cause all kind of imbalances and environmental problems that are increasingly difficult to manage. So is it possible in the future to decouple this? Can we continue this growth here on this side, but with not so steep growth or even a flattening out of the total consumption? Now, the problem is, of course, that this is the global average, but on a regional basis or even on a national basis, this looks very different. So here we look at the cropland nitrogen budget. So it's the surplus or deficit, and depending on whether you remove more or less from a field or from a country in this case, So, and you can see that we have red zones in the world where we have a lot of surplus. We're applying too much nitrogen. So here in parts of the US, in most parts of India, and parts of Europe, China in particular, excessive rates, So that's where we often then also have the environmental problems. And then we have part of the world, the dark blue and blackish ones, where we have either a near neutral balance for nitrogen or a deficit. And even a neutral balance, in fact, means that we're probably mining the soil for that nutrient. And most of sub-Saharan Africa falls into that category. And we have a few parts here in Eastern Europe and the former Soviet Union where we have similar situations, and in countries like North Korea over here. So we have a global imbalance of nitrogen, and it's the same for other nutrients such as phosphorus or potassium. And the question is, how can we correct this global imbalance? And of course, in an ideal world, we could say, well, we just apply less nitrogen in those red places and move it all to the blue places, but that's not as easy. The second issue is then Africa as a particular problem, because we know that at present, nutrient budgets in Africa are extremely negative. So we have plotted this here for nitrogen, phosphorus, and potassium, and you see the same situation. So the crop and removal is the blue line here, and the input from fertilizer is the red one. So it is increasing a little bit for all nutrients, but we still have a big gap in terms of the removal. So we have apparently high nitrogen, phosphorus, and potassium use efficiencies. They're above 1. But what this essentially means is we're mining the soil, and that is not sustainable. And it's the cause, and a primary cause for why yields of crops in Africa are low. And so the question is, what would it take to double or triple these crop yields in Africa and achieve this with an increasing and balanced input of nutrients? So in the actual paper, we then discuss 8 more of these specific issues. So I don't have time to go through them now, but we'll come back to some of them when we talk about some of the things that need to be done to attack them. But they relate to a wide range of things: nutrient losses and waste along the whole food chain. How can we reduce those? What can we do in terms of closing crop livestock cycles better? Soil health. More nutritious food, greenhouse gas emissions, and of course, what does climate change do to how we should manage plant nutrients in the future? So lots of very complicated questions that we need to tackle, and many of them also require actually a lot more research to understand better. So we then believe that this new paradigm for plant nutrition needs to follow a food systems and circular economy thinking. It encompasses, to be more responsible, encompasses a broad array of scientific and engineering know-how and agronomic practices and business models and policies and so on, that affect the production, the utilization, and the recycling of mineral and nutrients. Not just one or the other, but all of this, the whole chain, And that would then allow us to develop more integrated, more targeted plant nutrition solutions that hopefully minimize the trade-offs between productivity increases, environment, and health. And on top of that, of course, these more holistic solutions need to be viable in the farming and business societies of different regions. It doesn't make sense if they sound good for scientists, for example, or policymakers. In the end, it needs to be successful for farmers and the businesses supporting them. So we then propose that this new paradigm has these 5 dimensions that are more or less already explained several times. So they're interconnected. At the middle sits, of course, productivity, also food production, and being efficient and resilient in that, also in terms of climate change adaptation. But at the same time, doing good things for the environment, for the nutrition and health, for soil health, and have less waste and recycling. So we feel that to achieve this within the next few decades, there would be 6 key actions. You can see those here. And I'll now talk about each of those a little bit more so that it becomes clearer what they mean. So the very first action that we call sustainability-driven nutrient policies and business models that need to be tailored to the specific situations in a country. And that means that we will have to have more specific targets and also roadmaps consisting of policies and technologies, how we manage nutrients in a particular country to achieve the desired outcomes. And that depends very much on where this country is right now in its nutrient use and its nutrient use efficiency. So this graph here tries to illustrate this in the form of, and again, we're coming back to this crop nitrogen budgets. So we can calculate nitrogen use efficiency as the ratio of nitrogen output over input, so outputs from any sources, primarily as grain or other crop that is consumed, and inputs, fertilizers, manure, fixation, atmospheric deposition in particular. So and then we can see that for most countries in the world, follow a certain pathway. So at the beginning of their economic development, so they start out with very low nitrogen fertilizer use, and so the crop yields are low. The efficiency appears to be high, but in fact, that situation, we are mining the soil. So then, as a result of agricultural intensification, fertilizer use increases, and that means crop yields increase too, but fertilizer use usually goes faster up than crop yields, and so the nitrogen use efficiency declines, and often in the past has reached a low point, a low value, at which we also have very high surplus and environmental issues. And you can see this is roughly where India is right now. China in recent years have started to move out of this bottom, so increasing nitrogen use efficiency again. And ideally, we want to reach a situation where we come close to the practical limit, about 80 to 90% of nitrogen use efficiency, because that would then allow us to also have very low surplus and therefore very low environmental risk. In Western Europe and North America, for many situations, we're already around this point here. There's still a little bit to go. And of course, Sub-Saharan Africa, because we don't use much fertilizer, sits right up here. Yeah. So the question is then, okay, how is this going to look like for every country based on where it is right now? What are the specific targets and solutions over the next human generation? So that's the next 20 years. Yeah. So we need also relatively simple indicators like this nutrient use efficiency or nitrogen use efficiency indicator that I explained, because we can calculate it relatively easily based on measurable or existing data on nitrogen outputs and inputs. You can see this over here. And then we can also define ranges where we want to be. So I've already said that if it is very high, so over 90%, it means usually soil mining. So we need to do more to avoid soil degradation. If it is very low, below 50%, then we have a very risk of inefficient use and environmental problems, eutrophication and whatever. And we need to do a lot more to optimize the actual fertilizer application. So we want to, from both ends, go into this desirable range, which for most situations is 50 to 90%. On a global scale, in the next 20 or 30 years, we would want to move from currently an average of 50% to about 70%, maybe in the year 2040. So every country needs to now, I think, in our opinion, have a roadmap for this, and the policies required to incentivize the right kind of technologies and behaviors and support farmers and business, and that will also have to be different. The second action is around how we can not just generate more knowledge-driven solutions and new technologies, but also upscale them so that millions of farmers are using them. So you can see the problem illustrated on those pictures here. This is one from Asia, and this is one from Africa. And even though these are very different environments, here you grow lowland rice, here you grow upland crops, the common theme is that you have tiny little fields. And each field has a different management history, different decisions made by a farmer. So how do you then not just maybe develop new knowledge and recommendations and tools that in principle could be used to make better decisions for each of these little patches, but how do you actually reach millions of farmers with that kind of information so that they can use it and that it really is also helpful for them? So that brings in the need to have more digitally supported advisory systems, but also business solutions that can really be utilized to bring this to farmers. So in my own work in the early 1990s, I started to develop a new concept which we called site-specific nutrient management for smallholder farmers, and it had a lot of the scientific knowledge embedded. So how do you make pre-emergence crop nutrient decisions? So before you even plant the crop, what do you need to take into account in terms of what might affect the crop in terms of yield, about the soil, and then translate that information into a decision on what fertilizer to apply in the amounts that you probably need to, and when and how and what form. Yeah. But then, of course, also during the crop growing cycle, between planting and harvest, you had several points in time where you could look at the crop and also diagnose whether it needed more nutrients, or nitrogen in particular, depending on how it was evolving. Yeah. So we developed all this and later also transformed that in very sophisticated scientific knowledge into simple apps for farmers. The Rice Crop Manager family of Erie is shown here, one example for India. The Nutrient Expert System, software from IPNI, now succeeded by APNI in Morocco, was based on the same principles. And we demonstrated in demonstrations and tests and with farmers, with thousands of farmers, that we could consistently get 10 to 20% higher yields, 10% less nitrogen fertilizer was used in these situations. So we had much higher fertilizer efficiencies, reduced greenhouse gas emissions and water pollution, had no soil mining usually, and often also less pests and diseases. So farmers also needed less pesticides to spray. And this was shown in rice, wheat, maize, and later on in almost over 20 different crops in China, for example, itself. So the science was very good, the performance was very robust, but now is the question, how can you bring this to not just a few thousand farmers, but actually dozens of millions or even 100 million smallholder farmers? So in rice alone, there's probably 150 million rice farmers in one crop across the world. And if you add others, you're talking hundreds of millions of farmers. Yeah. So it's not enough to do the science. It's a question of how we then scale it up. So we have some hope that maybe in the future, more data-driven artificial intelligence type solutions can play a role. So for example, one could conceive that for many of these things, we could almost take the human out of making decision and have tools that automatically pull in the right kind of data and then use machine learning and other algorithms to make immediate actionable decisions. So without humans having to answer lots of complicated questions or collecting data. So that's the future, and it could, in theory, lead us to self-learning fertilizer recommendations for even for small farmers. Yeah. So that's what I'm hoping for. That's where a lot of clever research can be done, but the technology for this is in principle available now. The third action is on closer integration of crop livestock farming and reducing food losses and therefore also nutrient losses and waste across the whole chain. Yeah. So you see a picture here, which is an idealized picture of how farming in the future could look like. We've had over decades a separation in many countries, specialized crop farms on one side, and livestock farming done in a separate way, often also in confined facilities, almost industrialized, So what would be good in the future, because we cannot all become vegetarians or vegans, livestock products are essential and very helpful, very high quality products for human nutrition. But it would be useful if we could produce them in a much more efficient manner. So use livestock for what they're good at, for example, grazing on grazing land, and crops primarily for processing for human consumption directly. So that would be the ideal cycle, with a little less, but some only going into livestock cycles. But of course, residues and also from the various processing chains and waste chains, bringing back everything that we can recycle. We could also potentially recycle some of that through bioenergy or other bioeconomy extraction processes to create more value. And then what isn't usable, going back into the agricultural fields or into the livestock feeding cycles. So that would also fundamentally close nutrient cycles. So you have fertilizers largely going on arable land with small amounts in grassland, but a lot of it would one way or another come back, and the leakages into water systems or into the atmosphere would be a lot less. Yeah. There's a lot of also possibilities now in terms of new technologies for recovering nutrients from different waste streams, for example, sewage sludge from cities or other bio waste, even from slaughterhouses. So various companies and lots of also startup companies are working in that space. And so if you can do this in an economic way, then it's a new way of creating new kinds of fertilizers by extracting nutrients out of these waste streams towards a more bio-based economy. So lots of possibilities there that would fundamentally increase the nutrient use efficiency across the food chain. The fourth action of the new paradigm that we propose is that fertilizers in particular need to become an integral part of nutrition-sensitive agriculture. So we know that through targeted enrichment of fertilizers with specific micronutrients, we can have a direct impact not just on crop nutrition and crop health, but also on animal health and human health. So iron, zinc, selenium, and iodine are examples. And you see on the graph on the right is probably the most famous example so far. About 15 years ago, no, more than that actually, in the 25 years ago or so, the government in Finland decided that all fertilizers in Finland needed to be spiked with a little bit of selenium because selenium deficiency was widespread in the Finnish population. You can see this point here. So from then on, fertilizers had to mandatorily have selenium, and so the grain selenium concentration in wheat as a staple food went up substantially. And you could very quickly, with some delay, find a subsequent increase in the selenium concentration in the blood plasma of the Finnish population. So, and there were some ups and downs, but basically, you can see the relationship between these nutrients, in this case selenium, in the grain and in the blood until today. So we think there's a lot more possible to do in this space, particularly also in terms of attacking malnutrition problems in many lower income countries. So zinc is another good example. There's very good experiences, for example, on zinc fortification fertilizers or foliar sprays in Turkey with wheat. So, but the question is really, where is this most suited in terms of the nutritional problems and the soils? And who's going to pay for it? So is it the fertilizer companies who are expected to add these nutrients for free to their fertilizers? Would it be the farmer who doesn't really gain anything in terms of crop yield necessarily, sometimes, but not always? Or should it be the consumer? Should this food that is more nutritious be a little bit more expensive? Probably also not, because then poor people couldn't eat it. Or should it be governments? So interesting questions that need to be solved, and don't have a clear answer to that one yet. The fifth action is on novel fertilizer technologies. It has two dimensions. Of course, there's always innovation going on in designing new fertilizers with higher efficiency, slow release fertilizers or controlled release fertilizers. We have lots of interest in nano fertilizers nowadays. Anytime there will be new products coming. But the other dimension is that the way we produce fertilizers is very energy intensive. So the fertilizer production of ammonia, for example, accounts, if I'm right, for about 1% of global greenhouse gas emissions. But we now have new technology at our fingertips that allows us to produce ammonia in these factories with a much lower carbon footprint. So blue ammonia technologies through various techniques allow you to already reduce the carbon footprint, but the biggest potential is in what we call green ammonia, where you use essentially renewable energy sources to make the ammonia, and where you can also can use it as an energy storage system for the growing hydrogen economy. It's very good to store ammonia in that form, and then you can split it apart, and it becomes hydrogen that could power engines, for example, in ships or other types of transportation. So this is the future. In Europe, the Fertilizer Europe Association believes that already by 2030, 10% of the ammonia could be produced in that manner. We believe that worldwide by 2040, 30% reduction in greenhouse gas emissions associated with fertilizer production might be possible. And that would be a significant contribution to mitigating climate change. The sixth action that we propose is accelerated and more open innovation systems for faster translation of new ideas into practice. So, of course, there is a general problem that, in our view, both in public and private sector, there's currently not enough overall investment in plant nutrition research. That's one problem. So we may have investment in some companies in more proprietary technology, or in the public sector in very basic, maybe molecular plant nutrition research. But when we look at investments in more applied research on plant nutrition solutions, it is very little. So there's a need definitely to have more investment. But there's also the question what to invest in. Are we investing into the right things? We have, for example, right now a lot of investment into biological products. For example, microbes or engineering microbes that could potentially fix a little bit more nitrogen. Attracts a lot of venture capital and also for startup company funding. But that investment doesn't seem to be in any relation to the actual potential impact of these technologies, or at least that's still more questionable, So, but there is another dimension, and that is, are we doing science and innovation right? And that is something that I, in my previous roles, also at Rothamsted and IRI, have asked myself a lot. And I use very simple definitions here. You can agree or disagree with those, but science is basically about discovery, ideas generation, and building knowledge. Invention is usually about making something that nobody has made before. And innovation is the process by which ideas, previous knowledge, and inventions are then converted together into commercially viable products or solutions. And this requires these can be translated into practice at scale. And scale is not an idea in the head of a scientist or a little laboratory. And that they can continue to be used and supported by a viable business model. So my concern is that what we often have in science is excellent science, but very poor innovation. So many scientists do not go that route or do not know how to do this or aren't getting enough support and guidance to really move their discoveries down the innovation pipeline. So in the future, I think in science, we can also learn a lot from some of the culture and approaches that is probably more typical in startup companies. So maybe we can call it the marriage of lean science and lean innovation. So this picture is from the Agile Biofoundry in the US, which is a consortium of nationally funded laboratories who work together on speeding up biotechnology solutions, industrial biotechnology solutions. But it shows the general process being followed in product innovation design work in startup companies. So you design something, you build it, you test it, and and you really want to test your most difficult assumptions first, so that you can also know very early on when something fails and you don't waste time on pursuing it. You learn from it, and you integrate all that into the next cycle. And in every innovation cycle, you scale up already one step so that you move much faster to the scale at which a scientifically thought through solution then needs to work and becomes an innovation. This doesn't happen overnight. And every scientific organization, including UM6B, of course, needs to find their own approaches for this. It requires a significant culture change and then also the necessary incentives for scientists to do this. And I believe you do already some of that, innovation thinking, and I only encourage you to do even more of that. And hopefully the next generations of students embed that kind of thinking, this entrepreneurship approach from the beginning into how everything they do in their work. So it is clear that this new paradigm cannot be implemented by one organization or even one sector. It is something that is requiring increasingly more coordinated action by all of the stakeholders in the nutrient chain. So the fertilizer industry on one side, of course, farmers and their advisors and service providers, traders and processors of food, retailers of food, and consumers. Along this whole pathway, you can see that the red arrows here are essentially on losses of nutrients or waste that can occur. And so we can recover and recycle a lot of that and bring it back to the farming stage or back to the factory stage. That's what the green arrows do. But we also need, on top of that, the right kind of supporting framework from policy, from science, from financial organizations and civil society. So it's not something that will immediately happen overnight, but at least if we have this more sophisticated framework in mind, we should be able to have more success in the future. And success in this way would essentially be called a new kind of societal plant nutrition optimum, where everyone in this graph here is satisfied with how we manage nutrients in this world and also appreciates their value. So, we could then, within the next 2 decades or one human generation, have much more accepted standards for nutrients along the whole chain and also targets and roadmaps. We would hopefully have decoupled yield growth from growth in fertilizer use, and our global average nitrogen use efficiency may have risen to 70% from currently about 50%. We should be able to reduce nutrient waste in half and have also no more hotspots of pollution. We should have made huge progress and probably eliminated the extreme forms of malnutrition, including through the more targeted use of fertilizers. We must have reduced greenhouse gas emissions from fertilizer by at least 30%, probably more. It would be hoped that consumers finally appreciate more of the importance of fertilizer and what it does to the world, and doesn't see it just as something that is dangerous or polluting or whatever. And most importantly, that farmers then really have, every one of them, access to the right kind of tailored plant nutrition solutions. So what does this mean for Africa? Africa has its own very significant challenges that I think to a large extent are shown in this very simple slide, if you wish. So we're comparing here Asia and Africa. So the green dots are Asia, the red ones is sub-Saharan Africa, and the other ones are for a number of countries in Africa. And you can see the change in land area on the x-axis, with the early 60s set as 100%, and the change in cereal yields on the y-axis. So in Asia, during those 60 years shown here, we have essentially had an increase in cereal yields more than tripled, nearly 3.5 times. But the land area used for growing these crops only increased by about 25 or 30%. So really much more intensification has happened already. In Africa, you can see that yields have increased also, but they have not even doubled. But at the same time, the cropland area that is needed for producing food has more than doubled. And obviously, this cannot continue. because where are you going to find this land to feed Africa? Where would you chop down even more rainforest or other natural ecosystems? This is not a sustainable development path. There are exceptions. You can see Ethiopia rising up here with a slope in intensification or crop yield growth, and that is similar to Asia. But you also see countries like Mozambique down here where nothing has changed over the last 60 years in terms of crop yields, but more and more land has gone into cultivation. So it is very clear to me, and hopefully also you and many others, that the primary intervention in Africa needs to be, or one of the primary interventions needs to be, an increase in fertilizer consumption, but in the right way. We've made a little bit of progress. In the last few years, fertilizer consumption or rates, N, P, and K together per hectare, kilograms per hectare, have risen in sub-Saharan Africa, excluding South Africa, are now averaging about 20 kilograms per hectare. But realistically, that is only a tenth or less than in many other parts of the world. And there are only 4 or 5 countries in Africa where we have rates exceeding 50 kilos per hectare, which is still a very low rate because this is all the nutrients together. Bernard van Lauwe and I last year wrote a little paper called Sustainable Intensification of Agriculture in Sub-Saharan Africa, First Things First, in which we discuss this a little bit more, and I will leave you with 2 slides here at the end from that. So this is a graph from Bernard, and it basically shows that, yes, of course, ultimately we want to achieve a very well managed landscape, the natural resources in the landscape we want to really manage in a very nice and ecologically friendly manner. But what happens first, before even thinking of going there, needs to happen here at the farm scale. And this is what is shown in this box here as a full integrated soil fertility management approach. So where we really need to, in stages, go from relatively poor current practices that have low yields and also low agronomic efficiency of nutrients or other inputs to a much higher level, and germplasm and fertilizer are the absolute 2 immediate ingredients. And of course, we want to also make use of organic resources that are available in an integrated manner to add even more to this, And if we are able to then fine-tune things, agronomic practices very well to local conditions, then we should be able to achieve even more, So, but there's no way around this process. There's no shortcut. So if you forget about any of these ingredients, it's very unlikely that you will make this progress, and therefore also impossible to even get to any of these other nice things that you would like to do in your farming landscape. And so the lessons that we summarized in this paper were, well, the first one, smallholders need immediate returns on their investments. It doesn't make sense to invent ideas also in science or promote things to farmers that may have some return to them in 5 or 10 years at best. They need immediate payback. Otherwise, it just will not be successful. It's not beneficial for them, and there will be no wide adoption of it. The second lesson, sustainable intensification cannot happen without the use of fertilizer. There is no place in the world that has achieved this without fertilizer. It just does not work. So there's also no country that I'm aware of that has achieved higher levels of food production and food security, self-sufficiency based on pure low-input agriculture or organic farming. It does not exist. And Africa is no exception from this rule. So fertilizers are the essential and first ingredient. They just need to be available and they need to be used in the right manner. The third lesson is that fertilizer then, of course, needs to be combined with other agronomic improvements, or in simple terms, it doesn't make sense to throw on a bag of urea or other fertilizer if your overall agronomic management is very poor, if your soil is highly acidic or has other constraints, if you have very poor seed. So you need to make fertilizer part of an agronomic improvement program of good practices at scale. That brings in also questions such as suitable forms of small-scale mechanization or even suitable forms of irrigation. And the last lesson then is that once you've done these things successfully, you can start thinking about additional investments in technologies that target environmental services. They can follow profitable increases in crop yields, but not vice versa. And we say that because often also by many foreign organizations, things are being promoted that may sound right from an environmental point of view, or even sometimes from an ideological point of view. They may represent a certain value system of those promoting it, but they are not at the right stage of development. You can do this once you have a more successful farming system. And then, of course, these types of achievements can be added to it. And with that, I'm at the end of my presentation, and hopefully we still have some time to answer some questions.
Hey, thank you very much, Professor Dobermann, for this very insightful presentation. And I'm sure that many people found it very interesting. As you may have seen, we had over 116 viewers for this session, which translates the huge interest of different people from different countries in your presentation. So without further ado, let me just dash through the chat box and post certain questions for you. I will go from the beginning. Yes. The first thing is this, many people ask us whether we can share with them your presentation.
Yeah, sure. Okay. Yeah.
Okay.
I'll
great.
send it.
Yeah, thank you. Okay. And yes, greetings from all parts of the world. Yeah. Yeah.
A lot of greetings here.
yeah. A lot of greetings. Yes. And here is one. Here is a professor who knows you, maybe. He says it is always a pleasure to listen to you.
My good friend R.K. Singh.
Yeah. Well, glad to have him here. Yeah. I guess here is a first question by Professor Lamari, who is an INRA researcher, and he's teaching in the Fertilizer Science and Technology Master at UM6P. And he says, is it still possible to improve nitrogen economic use efficiency by combining nitrogen use to other technologies such as varieties, or in the case of integrated crop livestock production system?
Yeah, no, I think the answer is clearly yes. So there are various ways of increasing nitrogen use efficiency. One is, of course, how you apply the fertilizer, how much and time, the right form, and so on. Yeah. So, but of course, the crop itself, and therefore also varieties, differ in that to some extent. Yeah. I think breeding has not been hugely successful in breeding varieties that have consistently higher nitrogen use efficiency. There are some good examples, for example, with oilseed rape in Europe, I'm aware of. Yeah. So compared to the actual fertilizer management, the impact is a little less, I would say. But the key issue is that you need to have varieties that can utilize the nitrogen and other nutrients effectively. If they can't, then the efficiency will be low. And in the case of integrated crop livestock production systems, absolutely right. This is part of what I was trying to say with the closer integration of the both. So if we can make more use of feeding material that is more directly accessible, particularly grazing land and how it is being managed. So if we manage pastures better and have not just more biomass produced in pasture, also more nutritious biomass, then typically also the digestion of that in the animal becomes improved. And so the overall system level nitrogen use efficiency of a crop animal system of this kind will also be improved significantly. These things go hand in hand, and they are part of this thinking. Yes.
Okay, here is another comment by Dr. Richmond Dogby. I guess he belongs to APNI. Do you know him? So I have so far used mooring extracts to produce tomatoes and trying it on pepper as well. I don't know what he's talking about. Do you have any idea?
No, I don't know.
Okay, we'll ask him to explain what that.
Moringa maybe.
Is knowledge with us. Maybe moringa. Yeah, that's what I thought.
Oh, yeah. Well, it could be moringa. But I know nothing about it, to be honest. But there is a lot of interest in biostimulants of various kind, and they typically are plant extracts or plant-based materials. The problem with them is that for almost all of them, we don't really know how they work, if they work. And there's no consistent way of evaluating their performance. And also from a policy point of view, they are not regulated very well. So there may be some among them that work for whatever reasons and have a benefit, But there's, of course, also the risk that something gets sold that we might call snake oil, so potential cheating, Yeah. So I would always argue that, okay, so if these products are shown to have a clear benefit, then it's better to do this through a proper scientific approach, rather than just sort of believing, okay, it seems to do something nice, the crop looks greener, but that doesn't always mean much, So I would prefer a more robust scientific evaluation of that.
Yeah, he comes back with another question. He says, in Africa, for that matter, Ghana, it's obvious the more you try to better or load the fertilizer with the right micros makes the price unattractive, therefore not patronized. What can we do?
It is true that a big problem is that the price of fertilizer in most parts of Africa is much higher than other parts of the world. Yeah. So, and that is has many reasons. So there are infrastructure differences, or transportation costs are higher, particularly inland, and so on. So, and I think it is one of the fundamental issues that needs to be overcome from an investment point of view, to actually make these fertilizers accessible for farmers. And then, of course, asking the question, what is the most efficient and also economically beneficial way to use them, the right way to use them. So, but that current situation should not be taken as a justification to say, well, we don't need fertilizers, because in the end, plants need nutrients, and they need to come from somewhere. And if you want to grow plants successfully, you need to provide these nutrients. Now, of course, if you have large amounts of free or cheap organic fertilizer or manure at your disposal, you may do this. But the problem is that most farmers, as far as I know, won't have access to that and end up with having very poor crops with no nutrients. So, and that's where fertilizers come in, and then becomes largely an issue of can we in the future, through appropriate investment, but also through smart policies, And I'm not talking about eternal subsidies that lead to corruption or misuse of fertilizers. I'm talking about smart policies that enable it for farmers to get access to fertilizer at prices that they can afford and at the time when they need them.
Okay, thank you. Here is another question by our friend Professor Lamari from Universitat in Morocco. He says, in Africa, raising the issues of the efficient use of nitrogen in relation to human nutrition is still far from being a challenge for research in Africa. We are still facing food security problems first, he says.
Yeah, but that, yeah, you're right. That of course goes hand in hand. To be honest, the primary role of nitrogen is more food production. Yeah. So more calories. Yeah. But of course, it also plays through that a role in providing protein, because if you increase wheat yield, you also produce more protein through the wheat. Yeah. But what I was referring to in terms of human nutrition examples is largely related to some forms of micronutrient malnutrition, and whether one can use specific enrichments of fertilizers to particularly address those where they exist. They don't exist everywhere, of course. Yeah. So I'm not advocating to say, okay, every fertilizer needs to now have zinc, iron, selenium, and iodine in it. No. I think we need, there's a clear scientific basis for where these things are required, and that they can play a role in addressing specific human nutrition problems.
Okay, good. Another question by Dr. Sahib Abdurrahman. I guess I hope I'm pronouncing that very well. What is the best way to apply foliar applications or add as solid? And when we applying as foliar applications? I guess he's referring to nitrogen, maybe. Yeah.
So yeah, I mean that very much depends on the specific crop and environment you're working in. Yeah. So if you have soils, for example, just to take one example, if you have soils that are highly calcareous and have a high pH, typically then applying zinc fertilizer or zinc as a solid fertilizer will not be very efficient, because it gets absorbed in the soil and not available to plants. And then in that case, foliar application is much more effective. That's what's being used in Turkey, for example, on wheat. And so the problem with macronutrients is that the amounts that you need for a successful crop and higher yield are often quite a bit larger than what you could apply on a safe basis with foliar applications without burning the leaves, for example. So you would want to apply, I think, nitrogen, for example, mostly as a solid fertilizer or in the soil, and only supplement a little bit later as a foliar or other nutrients that require that. So it's a combination of the two that I always recommend. And in some situations, you need foliar applications. In some situations, it's not very effective. So, for example, if you have a very humid climate in which every afternoon you have a heavy rainfall, the effectiveness of foliar application will also be less. So lots of considerations there. But I think an integration of the two is useful where it makes economical sense. Typically, foliar applications in the end on a nutrient basis tend to be more expensive than solid applications through the soil too.
Okay, good. Here is a question, I guess, from Africa. Why not invest integrated nutrient management in Africa? Too much fertilizers are causing problems in the environment.
Well, that's exactly what I said. So the integrated soil fertility management is essentially integrated nutrient management. So you use as much as possible the organic resources that you have, but then integrate fertilizers along with this, because the organic resources alone will not be enough. Or can you tell me where all the farmers in Tanzania will get several tons of manure for their crops from, and at the right time and at the delivered to their door. That's simply not available. And the other problem that you have is that where do the nutrients come from that go into the manure, right? They need to come from somewhere too. So what you feed the cow is based on nutrients, and so if you feed the cow on nutrients that are grown in one place and put it back to another place through the manure, including what's lost, you always have losses. You put it back less, but you're also depleting the places where you've grown it. So it's not one or the other. It's the good integration of both. And that has been shown all over the world, that the integrated use of mineral and organic fertilizers is the best way forward if you have organic fertilizers at your disposal. The problems in terms of the environment only come if you apply far too much fertilizer or in a far too wrong manner. So I think in Africa, we are far away from that situation. There are very few situations that are really of this kind, and in general, it becomes a question of knowledge, better extension systems to avoid these kind of problems. We often also hear that nitrogen causes soil degradation or decline in soil health, these types of things. There's also a lot of misinformation on that out there, actually. So what happens is that if you have very high excessive rates of nitrogen repeatedly, of course, over many years, you may be decreasing your soil pH, for example. So you acidify the soil because of the nitrification process causing acidification. But that, again, is a matter of very high rates. And then, again, it's a matter of integrated management, that you basically provide other forms of amelioration to make sure that your soil pH does not decline. So it's not true that fertilizers are a poison or whatever. This is just misinformation.
Yeah, I agree too. Let us exhaust all the questions. Here is another can you share with us making techniques in the we are trying to promote this method? How the making of compost is still very laborious.
So I think you can find lots of compost making techniques on the internet. You just search and you will find all kind of recipes that people use for this. I make compost in my garden too. I throw all my bio waste on that compost pile and then just let it sit there and turn it around occasionally. And 2 years down the road, I'll put it back into my garden plots. So that's my solution. I don't add anything to it. I don't add earthworms or other biological cultures. I just let nature do the job. But I can do this because I have bio waste. I have garden waste and kitchen waste that I throw in there. So, but you need to think yourself, and you've already said it. It's very laborious. So, how much compost can you realistically produce in that manner? And where you're going to get all the bio waste from to do it, to really then have big amounts. But there are good examples also on the internet, I'm pretty sure, where even small entrepreneurs have become pretty successful in commercial scale compost making or organic fertilizer making or organic mineral fertilizer making. So I encourage these things because it helps with recycling waste, bio waste that otherwise wouldn't be processed properly. So, and compost, if it's done well, is a good product. It still doesn't have very high nutrient concentrations. Let's be realistic. So, but it certainly helps improving the soil and puts organic matter back into it too. So. But don't ask me about specific techniques. You can find plenty on the internet, I'm sure.
Okay. Yeah, there is another question from Mr. Ali Tiam. I don't know whether the same is the same Ali Tiam I knew many years ago, maybe a few decades ago. But he asks, fertilization has been renovated, especially mulch plastics. What do you think? And do you believe that it will be useful to Africans since pulpit has harmful consequences?
Yeah, I'm honestly skeptical too. So I've seen plastic mulching a lot in China. As a technique to primarily cover the soil so that temperature in spring is higher, so your crop emergence is faster. You have no weed problems, and you conserve more soil moisture, so you need less irrigation. But then, of course, the question is what happens to that plastic mulch? So you're creating quite a waste problem. Even though there are nowadays there are already biodegradable mulch products available in China, I'm not terribly convinced that this is the way forward. I would think that maybe it has a place in higher value crops. So if you have the ability to grow vegetables, for example, or flowers, because you have a good local market for that, then that type of approach might work, because it tends to also improve the quality of the produce. So, but for sort of bulk commodity agricultural crops like wheat and maize and rice also, I'm not convinced that this is necessary.
Okay, maybe I will take a last question, and that's from my colleague, Professor Muiz Am. And he says, from plant breeding perspective, what could be the contributions of plant variety in this new paradigm for plant nuts? Yeah.
Plant nutrition.
I don't know.
Plant nutrition.
Plant nutrition, yes. Okay, I'm tired. So talking here about varieties with high uptake and efficient use of plant nutrients. Professor Muiz, you need to be precise and clear. The message must be complete.
No, I understand it. I got it. Yeah,
okay, so, that's good. Great.
Yeah, I think plant breeding, with a few exceptions, has never really sort of very specifically looked at nutrient-related traits as part of a mainstream breeding program. And there are some exceptions. There's been a lot of work. For example, Jonathan Lynch's work in Pennsylvania on root traits in grain legumes, beans, and whatever, but it has all been very, very specific and very good science. But then bringing this successfully into a commercial scale breeding program that leads to the release of varieties that have traits that either increase the uptake efficiency at the root level, or through the root system, or have a higher internal nutrient utilization efficiency. So the amount of biomass, above ground biomass produced per unit nutrient taken up and stored in the plant, So really translating that into traits of that kind and screening for varieties or breeding varieties and screening them robustly for this has not been so successful in my opinion, So there are certain processes that I believe are interesting. So for example, we know that some varieties, I've seen this in maize and in rice, seem to have the ability to translocate more nitrogen in the final stages of grain from the leaves and stems to the grain, So a higher translocation efficiency, you can even see this visually. The plant is firing up from the bottom, mobilizing the resources to fill the grain, And that results then in a higher nitrogen harvest index and then higher internal nitrogen use efficiency. I always felt that, it would be really good if one could systematically breed for varieties of that kind, but it hasn't happened on a wide scale, And at the root level, I think the nutrient that people have been mostly interested in, besides some micronutrients like zinc and iron, has been phosphorus, because we know that we have lots of phosphorus sitting in the soil in recalcitrant forms that are typically not easily available by plants, but plants use many mechanisms to mobilize it. But then they also expend energy on that, which could cost some yield, So is the extra benefit from mobilizing that phosphorus then enough to compensate for the energy consumed in the process? So these are questions, but for me, a lot of good research has been done. The real challenge is now to demonstrate that one can move that into breeding programs. And that would be really cool.
Yeah, I thought that was the last question, but then when I went on the chat box, I found so many. And I don't think we have time to take all the questions unless you take few more minutes for your more questions.
Now we can take a couple more, but then I think it's enough.
Okay, especially when there are young researchers like this one from Diop Masamba. What's the potential of full ISFM in terms of filling the gap between actual yields and potential yields in Africa? That's an interesting question.
Yeah, I think it's a huge potential. So of course it depends a little bit on how you define potential yield. So typically we define it as the yield that is achievable with the available water supply. So attainable yield, if you wish. So your potential yield could be much higher if you had irrigation, for example. That makes a huge difference in how big your gap is between the actual yield. So if you were able, on top of the ISFM, to maybe put a low pressure, low cost drip irrigation system, solar powered, let's say, then your gap immediately jumps up and your success of the ISFM will also be much higher. But generally speaking, I think it is one of the most important interventions to work on. And the key for me there is to make it doable, make it feasible for farmers, to easy enough to do it. The full range of integrated soil fertility management.
Okay, here is another question from a very well-known researchers at In Morocco. Dr. Rashid Marabat. He's thank you for the excellent presentation, and he's asking, what do you think? Do you think that the Abuja commitment can be reached?
Well, the truth is it has not been reached. We're far away from it, and only a few countries have actually reached it at that 50 kilograms mark. So since last year already, there are discussions going on for organizing an Abuja 2 summit, or whatever it will be called, to precisely come back to this question and ask, okay, what do we need to do to really achieve it now, or even more, because what was originally agreed on is probably not even enough. So I think we have seen some progress, as I also said, in some countries even more than others, but it's by far not enough. And that's a political problem, but it's also an investment problem. And I have to say, of course, also in the industry that I now represent largely, there's still too few players who really seriously look at the African market and invest in it. There are some big exceptions, OCP in particular, which is probably leading in its efforts in Africa, and a few others. But we need a lot more commitment from many others.
Okay, there are plenty of questions. I think we will stop there. We'll keep it there. We will thank you very much for this very interesting presentation that has sparked a number of questions. And I would like to take the opportunity to thank our participants and viewers for their interest in our webinar series. And we are now at the second webinar, and we still have 8 more to come. So be there. And before I close this, I'd like to make some announcements about our fertilizer science and technology master degree at UM6P. The closing date for receiving application is on May 31st. And if you are interested, you can start your application on the website, on the my.um6p.ma site, or if you need more information about this FST master, you can drop an email at ESAFE or drop a WhatsApp message to the number on the screen. Otherwise, you can go and visit our esaf.um6p.ma. With that, I will thank you very much all for your interest and for your perseverance, and let us all thank Professor Dobermann for sharing his knowledge, and I will solicit him to post to share with us his presentation so that we can mail it to all the people on our mailing list. That will be a great educational tool for everyone. Thank you very much.
Thank you. My pleasure.
Yeah, merci beaucoup.